Hello and welcome to this video. We're going to be working with um, exponential functions for growth and decay in this week, week 9. We're going to start off with section 5.7, which covers financial models. We're going to be looking at some compounding, continuous and by rate period. So this is the formula that we're going to use for compounding with a given growth per rate period. That rate period is going to be n, number of times of interest compounded per year. So n is going to depend on whether we do a monthly. In this example, monthly means n is equal to 12 times per year. T is time in years, R is interest rate, and we're going to write that as a decimal. So if it's 6%, 6% is going to be 0.06. In our formula, P is principal, how much you invest, and A is future value. So here's an example that we're going to use this formula for. We're going to invest $50 at 6% compounded monthly for a period of 3 years. So we would have A equals 50 times 1 plus 0.06 divided by 12, and our power would be 12t. Actually 12 times t, and t is actually 3, so it would be 12 times 3 in this case, because we do know the number of years. So we can actually figure out how much is in the account, or how much the future value of this would be after 3 years using this formula. Alright, and we would just stick this into our calculator, and it would tell us our let's type it in here, 50 plus times 1 plus 0.06 divided by 12, all raised to the power of, now we should put that in parentheses so we get both of them as a power. 12 times 3, which is 36. We could just type in 36 also, but this would be my solution. So we're going to say the future value of this is $59.83, because that's what we got there by just plugging it into the calculator. Now this is in this section because what we're going to be looking for here is we're going to be looking for this. This is going to be what we're going to be looking for in the future, is t for time. We're going to ask how much time it's going to take for investments to occur. In order to do that, we're going to need to use logarithms to help us solve the equation. So something like this we can just plug in. If we have all the values, we can plug that in and find the future value. What we're going to be looking at is an example like this one, where we're finding the value after a certain amount of time. We're starting with a starting value and we're ending with this value. So let's take a look at that problem. Let's move it up a little bit. So in this problem, we're going to invest $3,000, earning 6% compounded monthly, and we want to have it have a value of 5,000. That means we want the future value to be 5,000. So in this case, we're looking for time here. How long does it take? We're looking for t in the formula. So in our formula, here's the formula again. Looking in the formula, we're going to have everything except for t. So when we write that out, we're going to have our future value, $5,000. We're going to have our present value, $3,000. We're going to have our interest rate, 6% again. We're going to have how many times it compounds, compounding monthly. So that's going to be 12. And we're going to end up with 12 times t here, because that's where we don't know the value of the time. So everything is in the formula except time. And that's what we want to try to find out here. So we're going to use logarithms to solve this. So my first step here would be to divide by the 3000 to make it a little simpler. So if we divide both sides by 3000, we get 1 plus 0.06 over 12t equals, we can reduce this. I'm just going to write it as a fraction, 5 over 3. I don't want a mixed number or a decimal there yet. Now, I think 0.06 divided by 12 is a nice, or it's a decimal. We're going to just plug that in next. 0.06 divided by 12. I think I know what that is. It's 0.00, yep, 0.005. So we can rewrite this as 5/3 equals 1.005 to the 12t. Because our decimal here was 0.005, and we're adding that to adding that to 1. Now, this is where we would use a logarithm to solve, because we want to try to solve for this. Now, there's two ways to do this. We can, the way I'm going to use here is I'm going to apply the logarithm to both sides. Now, I'm going to use natural logarithm. Actually, in the book they use natural logarithm. I'm just going to use a regular logarithm here. So log, this is the same as applying the natural logarithm. You'll get the same results. It doesn't matter which base. So I'm just using one of the bases that I have on the calculator. I have one of these two bases. So I have to use one of those logarithms when I do this. So we applied the rule. We applied logarithm to both sides. Now we do that because now we can use the property of logarithms that says we can move this in front of this logarithm. So now we're going to end up with 12t times the log of 1.005 equals the log of 5/3. Now we could write out the log of 5/3. We can expand that out, but we're just looking for a number here. So I'm going to leave this as is, and we're just going to apply that in our calculator. Okay, so if I rewrite this just one more time, this is t times 12 log 1.005 equals log of 5/3. Now all I need to do is divide to solve this. I just need to divide by 12 log 1.005. I need to divide this by 12 log 1.005. Now that's what t is going to equal. And we can get that number in our calculator just using our log button as our. Now I'm going to use parentheses because I have a 12 and a log, so 12 times log 1.005, two parentheses. Okay, so this should be my answer. So we're going to say t is about 8.54 years. So it's going to take a little over 8.5 years for this value to grow to 5,000. Now if we use a rule of 70, we can get an approximation too. The rule of 70 says we can approximate what it would be at 6,000, so it should be less than that. So you could use a rule of 70 to help you verify this answer. You could also take the 8.54 and plug it back into the formula right here and see if you get 5,000 or close. It'll be a little bit off because of the rounding of the decimal. Okay, it'll be a little low because it's not, we didn't, oh well, it'll be a little high because we rounded up. Okay, now the last thing I want to do here before we move on to this other thing, these other continuous compounding, is I want to look at we want to be able to compare interest rates. So in order to compare interest rates, we need to be able to figure out the annual interest rate or the yearly interest rate. So in order to do that, what we would do is use this formula. Remember or you might want to know that this is going to be, when we do this formula, P A equals P1 plus R over N, and T is very close to this formula here, which we will do in the next video. A equals actually it's going to be Y equals, sorry, whoops, we scrolled, I wanted to erase and I did not. Let's see, here we go. Y equals AB to the X power. So we're going to use this in the next video. What we're saying here is that this part of this formula right here through up to this point is going to be the letter B here in this formula. So that means that to do that, we separated B here into 1 plus the growth rate before. 1 plus the growth rate, or 1 minus the growth rate if it was decay. So what we're saying here is we want to write this so it's similarly. Well, we have the 1 plus here. So what we want to do is we want to evaluate this to figure out the growth rate. So if, for example, I want to figure out what a 6% compounded monthly interest rate would be for a yearly interest rate, yearly question mark, I would just use this formula, just this part, and say I would do 1 plus 0.06 over 12 to the 12th power, and that would give me my interest rate, which is 1.005 to the 12th power. In this case, it would be 1.0617. So basically this is our growth rate per year, which is 6.17% per year. So what we can do is we can get all of these to compare. If I wanted to do a comparison between a monthly and a daily one, I would use this part of the formula to rewrite it so I can compare it in yearly rates. Now, when banks do this, they always do yearly rates because they're always higher than their monthly rates and daily rates. So they like to say, oh, we're giving you the best interest. So they want to give you the yearly interest rate. All right, now I want to finish this video with a continuous growth model. So this is the continuous growth model. The letters stand for the same thing, except for E is your number letter on your calculator. That's 2.718 approximately. So we write the formula the same way. We have in this case we have $10,000. We're investing at 4%. So it'd be 0.04 for a continuous compound. It says continuous on there, and this would be my formula. The formula simplifies a little bit because we don't have an interest rate per time, but in this case we have it continuously, so a continuous rate would be put above the E value here. Now we're going to do an example like this. Hopefully you'll see the same method happens here. Now in this case we got 80,000 equals 25,000, e to the 0.07 to the t power. We're going to divide by 25,000, and then we're going to take the natural logarithm. So it's 80 divided by 25, which reduces. We're going to take the natural logarithm on both sides. Now these two are inverse functions, so they drop out and you just get 0.07t equals ln of 80 divided by 25. Now we just need to divide by 0.07 to get the answer. So try that out and see what that is, and we'll call it good for this video.